To finish things off, I want to tackle one more type of function, trigonometric functions. And in particular, let's focus on the sine function. So for this section, I'm going to assume that you're already familiar with how to think about trig functions using the unit circle, the circle with a radius 1 centered at the origin. For a given value of theta, like say 0.8, you imagine yourself walking around the circle starting from the rightmost point until you've traversed that distance of 0.8 in arc length. This is the same thing as saying that the angle right here is exactly theta radians, since the circle has a radius of 1. Then what sine of theta means is the height of that point above the x-axis. And as your theta value increases and you walk around this circle, your height bobs up and down between -1 and 1. So when you graph sine of theta versus theta, you get this wave pattern, the quintessential wave pattern. And just from looking at this graph, we can start to get a feel for the shape of the derivative of the sine. The slope at 0 is something positive, since sine of theta is increasing there. And as we move to the right and sine of theta approaches its peak, that slope goes down to 0. Then the slope is negative for a little while the sine is decreasing, before coming back up to 0 as the sine graph levels out. And as you continue thinking this through and drawing it out, if you're familiar with the graph of trig functions, you might guess that this derivative graph should be exactly cosine of theta, since all the peaks and valleys line up perfectly with where the peaks and valleys for the cosine function should be. And spoiler alert, the derivative is in fact the cosine of theta. But aren't you a little curious about why it's precisely cosine of theta? I mean, you could have all sorts of functions with peaks and valleys at the same points that have roughly the same shape, but who knows, maybe the derivative of sine could have turned out to be some entirely new type of function that just happens to have a similar shape. Well, just like the previous examples, a more exact understanding of the derivative requires looking at what the function actually represents, rather than looking at the graph of the function. So think back to that walk around the unit circle, having traversed an arc with length theta and thinking about sine of theta as the height of that point. Now zoom into that point on the circle and consider a slight nudge of d theta along their circumference, a tiny step in your walk around the unit circle. How much does that tiny step change the sine of theta? How much does this increased d theta of arc length increase the height above the x-axis? Well, zoomed in close enough, the circle basically looks like a straight line in this neighborhood. So let's go ahead and think of this right triangle, where the hypotenuse of that right triangle represents the nudge d theta along their circumference, and that left side here represents the change in height, the resulting d sine of theta. Now this tiny triangle is actually similar to this larger triangle here, with the defining angle theta, and whose hypotenuse is the radius of the circle with length 1. Specifically, this little angle right here is precisely equal to theta radians. Now think about what the derivative of sine is supposed to mean. It's the ratio between that d sine of theta, the tiny change to the height, divided by d theta, the tiny change to the input of the function. And from the picture, we can see that that's the ratio between the length of the side adjacent to the angle theta divided by the hypotenuse. Well, let's see. Adjacent divided by hypotenuse? That's exactly what the cosine of theta means. That's the definition of the cosine. So this gives us two different really nice ways of thinking about how the derivative of sine is cosine. One of them is looking at the graph and getting a loose feel for the shape of things based on thinking about the slope of the sine graph at every single point. And the other is a more precise line of reasoning, looking at the unit circle itself. For those of you that like to pause and ponder, see if you can try a similar line of reasoning to find what the derivative of the cosine of theta should be.